Welcome to breadboarding. In the previous video we had a look at some of the detailed CUPL programming examples, and at the end I just showed that I managed to get one of the ATF750Cs, and that's where we left it. So this is part 4 of the Breadboarding Labs Programmable Logic Devices mini-series. And this video what I'm going to do is to cover how PLDs really work. So we're going to be looking at the fuses and terms that actually determine how these work. We'll have a quick look at the simplest PLD file and the JED output file that we can possibly make. Then we'll have a look at the JEDEC file standard, which is the JED file that we produce out of this. And this has been a standard going back to about 1983, and just explain what some of the fields in there so it actually makes a bit more sense to you. Then I'm going to be going on to have a look at the ATF750C. We'll just have a bit of a background look at the datasheet and some of the features it's got, and then we'll also just try programming it with one of the simple gates examples that we've used in the earlier videos. So how do PLDs really work? You'll hear the term about fuses a lot, and fuses came from the first PLDs in the mid-1960s. So according to the book I referenced in the earlier videos, which I'll include the link in the description below, then one of the first PLDs was actually a diode matrix from Harris Semiconductor in the mid-1960s. And you can see here I've highlighted from this extract, programming is accomplished by cleanly vaporizing a fusible link by application of a brief high voltage pulse to a selected array element. And you can see there's a little bit of the picture here where the fusible links basically would just get vaporized by the voltage, and the text actually says that compared to today's PLDs this was quite primitive. There were no commercial programmers available, so you either had to get Harris to do it or make your own, and the programming circuit allowed programming only one fuse at a time and required nearly an amp of current to blow each fuse. So things in those days were a little bit basic, and obviously they've moved on a lot since then, and the devices that we're using use flash programming, so they're erasable, and I think the latest ones are erasable up to about 1,000 times before you might start to run into problems with them. So let's take a look at the simplest PLD we can make and what the output files will be. So this is using the ATF22V10, so it's my favoured chip, and the simplest one here is just about as simple as you can get. So we have one input pin on pin 2, we have an output, and we're going to invert the output just to sort of indicate that we actually have something going on here. So pin 2 is defined as input. Pin 23 is defined as inverted output, so the invert on that pin will mean that it's using the pin polarity really to do that. And we're just saying that the output is equal to the input, and because we defined the output with that polarity, then it should do the inverting there. So I've already compiled this in WinCUPL, and if we have a look at the output documentation file, so you can see that we've got our output is assigned to the input, the output enable is defined for that, and then when we look at our symbol table here, we can see that the output does in actual fact have the pin polarity defined as negative logic. But then when we see the fuse plot here, we can actually see that we've got some of these numbers here. So this is the synchronous preset term here. And when we look at the data sheet, we should be able to find out where that is. So 5764. Now the X's and minus and signs in here are a little confusing. If we go down the bottom, it will tell us that X is where we're leaving things alone, and minus is where we've blown the fuse. So my mind works a little differently. I always think the X kind of is where you've blown it. But so X means we're leaving it alone, and the minus means we're clearing it. So we can see here, if we actually count how many X's we have here, starting at 0, down here we can see selected 44. So in actual fact, this is starting at the very first fuse. I think this is the asynchronous reset, and this is a synchronous preset, the two things here. But our pin 23 is actually starting here, so 44 is basically the one after this one here. And what we can then see then is that all of these have been blown, and it's only this one here. So this, if this is 88 here, 89, 90, 91, so this will be 92. So we've only had 92 left here, all the others have been blown. And you can see up here as well that we've got the mode for this. So this will be the S0 and S1 values here, and I think this will equal 0, 1 in fact when we come to look at that. And you can see that all the other ones here have pretty much been left alone, and we can see here in our pin output we've got the input there and we've got the output with the inverted polarity there. So if we have a look at the JED file that's produced, so this is the JEDEC output file, and we can see here we have our header information here, and then we have all this information down here. So there's some stuff here which I'll explain in a few minutes. Then we've actually got the link information here, and we can see that in fact that we've got one link here which is actually left behind. So what I'm going to do is to go back and have a look at the JEDEC file information, and we'll have a look at this and see if we can work out exactly what's going on here. So JEDEC is an industry body for electronics, and around 1980 there was a proposal to come up with a standard for programming PLDs, and I think it became a standard around 1983 according to the June 94 version of this document. It is available on archive.org. You have to be a member of JEDEC to actually get it through the JEDEC website, and I'll include the link for it in the description below. Just on archive.org, and this includes the information about the JEDEC standard. I'm not going to go through in great detail of it, but there's a few bits I've extracted from it, in particular this bit here. So there's a couple of odd things we do need to be aware of. So the file starts with the start transmission control character, which is 02 hexadecimal control B, I guess if you were doing it from an old-fashioned serial terminal, and the file ends with end transmission ETX, which is 03 hex, which again would be probably control C using an old-fashioned terminal, and those bytes generally aren't shown in most text editors. And then the information, in addition to the information from the JEDEC standard there is actually also some of the information on the file format in the WinCUPL help document I've created. So this is the CUPL reference guide that I've created and I covered in some of the earlier videos. So this is now just a PDF of the Windows help information that comes with WinCUPL, and in here we can see that down the bottom here it actually has something on JEDEC, so 197. So again, this includes the information about the STX, ETX, and also information about the various values and things that we'll have in here, which we're going to cover in a minute. So in that document it actually says the fuse link field L contains the actual data. Each device fuse link is assigned a decimal number starting with 000 that we've seen, and in some of the PLDs it does actually need to go above 4 digits. Each numbered fuse has two possible states. Binary 0 specifies a low resistance link, fuse intact, so 0 means leave it alone, and binary 1 specifies high resistant link, fuse blown. So the zeros in JEDEC mean leave it alone, the ones mean blown. And the legend that we had in the document file that was showing you showed an X is fuse not blown and a minus is fuse blown. So it works a little counter to the way how my brain works. Other people may be different, but so 0 is the same as X and means not blown, and 1 is a minus sign and means blown. So that can be a little tricky to get your mind around when you're switching between the two formats. And then when we look at the fuse plot information that I showed you in the doc output file, you can see here that we've got, these are all where the fuses have been blown, and there are just two entries left here, and the reason for that is that this is the second example I'll be showing you in a few minutes. If we look at the extract from the JEDEC standard, so this is the table with the information of interest. And here what I've done is I've taken one of the sample JEDEC files and I actually annotated it. So you can see at the top here, file starts with STX control B, file ends with ETX control C, and then these are the bits of the file that actually can be correlated over here. So QP means a number of device pins, so in our particular case it's a 24-pin device. Then QF is the fuse limit, and QV would be the test vector limit if we were using the testing instructions in here, but we're only using the fuse limit. So this actually refers to the maximum number of fuses in the chip. Then G0 is a security fuse, so 0 means don't set, 1 means set. So that means if it was set, you wouldn't be able to read the structure of the PLD. We tend to not set the security fuse so we can read the PLD back and check to see what the configuration is. Then this one's also quite important in the fuse default state. So F0 means that if there isn't a row defined in the file, so you see here for this one with 5,892 fuses in here, it's only got a handful of lines, and all the other ones can all be considered to be 0. And again, 0 means not blown, leave alone. And then down the bottom here we can see that we've got a fuse checksum starting with a C there. Then in fact the ETX I think goes after here, and then the file checksum actually comes outside of the ETX character there. So those are the things we actually need to worry about. We don't generally need to worry about it because WinCUPL takes care of all this stuff, but if you were trying to understand why something wasn't quite working, then this information could be useful. So if we go back to the JEDEC file that we had here, so we can see here that we seem to have something which is set here around this column here. This is 28 in, so this will be about, I think, 92, I think fuse 92. So fuse 92 is not set there. So if we actually go and look at the datasheet for this. So if you remember in some of the earlier videos, I covered some of the various output logic macro cell configurations. And in particular, if we're using the registers, the flip-flops, or we're using the combinatorial mode. And we're using the combinatorial mode in this particular case. And then this is the fuse map, and it shows really that all of the input pins, the output pins, so we're using pin 2 and pin 23 here, and you'll see that all these numbers here show the fuses, and so we'll look at which fuses we're keeping in this particular example. We can also see then that the S0 and S1 values on how this output logic macro cell is configured are also defined here. So what I've done here is I've taken an extract of this and I've worked it through. So what this actually shows, if fuse 92 is in fact the second line down here, if I just zoom in here, probably make it a little bit easier to see. So you can see here the first line is 44, there's 44 on each row, so the next one is 88, and in fact this is 88, 89, 90, 91. So this first one here is 92. And we can see that in fact this shows the route for pin 2 taking the normal logic, so this is not inverted, going straight along there, and then it's... So this is coming into our OR gate and will then go through our output logic macro cell. Now, as I said, the values on here we'll check in the documentation file. If you look at the doc file, we can see that in fact it was S0 is 0 and S1 is 1, because that's what the mode is in this particular output here. And what we can then see is S0 equals 0, S1 equals 1. If we go and have a look at the next page, you can see that in fact S0 is 0, S1 is 1. That means we've actually got an inverting output here. So if it was 1 and 1, we'd just have it going out without the invert. So this is actually what gives us our reverse polarity. So we know that in our mapping here that the output has actually got this polarity set here. So what this shows in the very, very simple case is how this particular example works. Now I did do a second example here where at least I also set the output enable on this as well. So let's just have a look at that. So the simplest version 2, this is almost the same. The only difference is we've defined the output enable active low there, and what I've also done, so we see here that we've got output enable is active low, and then we've also added the OE term to the output, so the output will be turned on and off by the value on pin 13. If we then have a look at the documentation file for that, see now we've got the polarity on the OE, meaning that it's the input from the pin is active low, but we only have to worry about the true value of OE within the rest of the rules and things. And now if we have a look at our plot here, we see that in fact we've got another item on this line 00044. If we go back to the previous one, you'll see there was nothing on that first line. So this X that we've got here is probably going to be related to the output enable term. So this is likely to be 87, I guess. Yeah, so the next one here is 88, so this will probably be 87. And if we go back to our diagram here, we can see that in fact 87 is likely to be the output enable term here. So this is output enable, and 87 is the 44 plus 43. This is 40, 41, 42, 43. And this one here, so it will be joining this thing here. And if we go back to the data sheet and we go down to the bottom here, we're almost certainly going to find that that will actually be coming from the pin 13 output enable. Yeah, and if we have a look here, we can see that in fact the inverted output of the pin 13 output enable is going into this line going up here. So in fact, that junction here is in fact the pin 13 output enable with reverse polarity logic actually setting output enable. So this just shows that the negative polarity input from the pin 13 output enable, because we had the exclamation mark and it defined, is actually coming up, joining to here, which will be 87, and then we're doing the output enable there. So it's a very simple example, but I think all that's happening when we're doing more sophisticated examples here is that we've just got a lot more fuse values determining where the various logic rules and things are configuring the PLD. So we've covered the simplest PLDs and the JED output files. We looked a bit at the JEDEC file standard, and again I'll include the links in the description below if you want to go off and have a detailed look at that. So what I'm going to do now is to have a look at the ATF750C, which is an advanced version of the 22V10 that we've been using, and I'm going to talk about some of the advantages of this chip over the basic one, and one of the big disadvantages as well. So the ATF750C is just really an advanced ATF22V10, so it's a 24-pin superset of it. You'll notice that the pin layout is almost identical. The only difference between this and the 22V10, there's no power down pin on pin 4 in this particular case. But it's only really when we get to look at the datasheet and some of the diagrams in it that we'll get to see what some of the big differences are. And the big difference is that each of the output pins actually has two sort of output logic macro cells, and it has two flip-flops. Each flip-flop has an independent clock and a synchronous reset. Still has a common synchronous preset, but I don't believe the preset is as useful generally as the reset. And it also includes both D-type and T-type flip-flops. T-type flip-flops can be more useful for doing sort of JK-type flip-flops, apparently. Now, the disadvantage of this chip, it is about 2.5 times the price of the ATF22V10, about 5 times the price of the 16V8. If we look on Mauser, so yeah, it's just under £5, probably about $6, I guess. So it's more expensive. So you wouldn't necessarily want to use this in all situations, but it is useful for certain complicated examples, which I'll talk about in a minute. But probably the biggest drawback is that the only programmers that I've found to work with this are the high-end ones or professional programmers. There is a YouTube channel from some electronics university professor talking about this, and I think he says that the professional programmers to do some of these chips and the ATF2500 are about $1,200, £1,200. Now, the XGECU T56 that I have was around this sort of price. At the moment it's £345 on Amazon. You probably can get it cheaper if you buy direct from China, but this has just been replaced apparently by a T76, which is about £307 on Amazon. So if we just have a quick look at those. So T56 is the one I've got. It does come with an awful lot of adapters, so it comes with a lot of adapters for a lot of surface mount chips and things. So it's not like you're only getting the programmer, but you do require this to be able to program the 750C. I have not been able to get my one to work with the ATF22V10 yet, even though it is on the compatible list. I may need to raise this actually with the manufacturer to see if there's any issue they're aware of. And then this is the T76, which has only just been released, and I think the XG Pro software was just released a couple of days ago, which actually supports this programmer. And this one is in fact a little cheaper. I'm not sure if it comes with quite as large a range of adapters as the previous one did, but certainly unless you need to use one of these chips, there's quite a big difference between 300 odd pounds for a programmer, and I think the T48 was about £60 that I said in the previous video. So you really would have to be absolutely sure that you want to use one of these. I'm sure it's worthwhile and it'll do an awful lot of other chips, just not the ATF2500 40-pin chip. I'm not going to go all the way through the data sheet. I'll leave that for another day, but there are a few key things we need to pull out of it. So in the combinatorial mode, you'll see that it's possible to either have separate terms. So these two cells here, which are part of effectively the cells for the same pin, are independent, and so this Q1 can be fed back into the pin array here, but all of the inputs here are separate, or they can be combined, and you can see that the output of this set here will feed into this logic gate here. Now the Q0 and Q1 outputs here do have their own pin nodes, which we'll come to in a few minutes. So it means that we can actually talk to each individual D registers here and configure the clocks independently. So we can have it coming from the synchronous pin 1, which is the same as the older chips, or we can actually define a clock term specifically to come into here dedicated to each one of these. So we've effectively got two flip-flops on each pin, so that means we've got 20 flip-flops in total. So that means we could do up to say a 20-bit counter, for example, using one of these chips, whereas previously with the 2210 you could only do a 10-bit counter, for example. And then if we're using the registered mode itself, you'll see here that in this combinatorial output, the output to the I/O pin is actually coming from here and from here, and the output from the register here can still be used to feed back into the rest of the PLD, but it isn't actually fed to the outside world. And then in the registered mode, then in fact the Q0 is going to the I/O pin. Now it doesn't go directly to the I/O pin, it still goes through an output enable buffer and can also be inverted as well. There's a stage which I'll show in a minute. And you'll see here that this one again is combined, so the inputs here into this OR gate are combined into this one, but this macro cell here can still work independently and be fed back through the Q0 and Q1. And this from I/O pin in fact comes from, it's not shown on this diagram, I'll show it in a couple of slides time, but in fact this output here goes to one side of the output enable buffer, whereas the I/O pin actually does come from the outside connection to the pin. And there's a slide to explain about this in a minute. So if we look at the dev help PDF, this is where all this information comes from. So in the dev help, you can see here it's under the V750B. There doesn't appear to be one for the V750C, but I believe that the values are the same. And you'll see here that it's a 24 pin count, 171 product terms. So that's the combinations that we can have in the matrix. But then you'll see the extensions here. There's more extensions available here. I'll explain about those in a minute. And then in addition to the inputs and the output pins, there's also these nodes for the Q0 and Q1 registers. So in fact, the one thing to note is that the Q1, which is kind of the one that's an internal one that's not connected to the outside world, has the range of pins 25 to 34, whereas the Q01, which is the one that is connected to the outside world in registered mode, has 35 to 44. Now you may need to use these if you were, for example, using combinatorial mode for the output, but you wanted to make use of the registers internally, for example. And then it also tells you how to do the clock assignments. So for example, if you refer to a particular pin with .ck, it will define the clock to be a specific term. Now the only thing is here is I've been playing around with this and I'm not sure you can have it to have a term like this. So I'm not sure WinCPO allows us to assign a expression like this to the clock input, certainly from my experience recently. And this one here is then telling us if we want to use pin 1, the main chip clock, then we set it to CK mux, and that basically just takes pin 1 just like it would have done in the original ones. The only thing to note is here, if we were using the flat package, the PLCC version, then the Q1 and Q0 node numbers are got 4 added onto them. So what does this actually mean? Well, what it basically tells us is the .D is a D-type flip-flop, the .T is a T-type flip-flop, AR is asynchronous reset, just like the previous chip. So CK is the new thing, and this is a real important thing, I'll explain in a minute, that being able to have a clock defined for each flip-flop allows us a lot more flexibility. The CK mux just allows us to use pin 1 clock for a particular flip-flop, output enable pretty much as was previous. Synchronous preset is common across all flip-flops, so it's not quite as useful. And then these two ones here, which I'll explain in a diagram on the next 2 slides. DFB is D-type feedback, but this is only really used when you're not having the output of the register going to the outside pin. It's for when it's a combinatorial mode, but you can still get the feedback from the register. And the input-output pin feedback, again, similarly, there's a circumstances when you may need to use that in registered mode. And then these are the Q0 and the Q1 registers. So Q0 was the default one at the top that is connected throughout to the output pin, and Q1 is kind of the internal ones. And these are the pin numbers you need to use to actually refer to these in some of the more exotic configurations. And this is from the CUPL reference PDF they produced from the WinHelp. And you can see why this WinHelp is actually quite important, because it does actually explain exactly what is actually going on here. So the DFB extension is used in special cases where a programmable output macro cell is configured as combinatorial. So basically we're just sending the logic gate output straight to the outside world, but we still want to make use of the registers for doing some internal stuff into the array. And so the DFB output here allows us to feed back the register value when the macro cell is configured in combinatorial mode, not in registered mode. So under normal conditions, when an output is configured as registered, the feedback from the register is selected. You can actually just select the output to get the feedback if it's a normal one. So that's what the DFB extension is for. And then the I/O one, this is the bit that I didn't show you on the datasheet. So all of the outputs on that datasheet. So this is the datasheet showing all of the pins and the output logic. And you see there's across 2 pages here. You see got our input pins, our output pins, but you can see that the output logic in the diagrams that I showed you previously, there's also this bit on the end of it. And in addition to the output enable here, there's also the feedback going back into the array here. And what this I/O extension is used to select pin feedback when the macro cell is configured as registered. So when we have a registered configuration, the feedback from here is normally coming from here, but if you wanted to take the feedback from the other side of this buffer here, then you would use the I/O. And you can see here this is actually showing the output from the logic cells is coming in here. Then depending on if output enable is enabled or not, then you're getting a value out of here or not, And you can see this is the inverted one and this is just the straight buffered one. But this point here where the orange is basically where the feedback for the .io is coming from. So it's probably a rare case that you would want to do this, but there are situations where you need to do this. So it's a much more sophisticated chip, and what I'm hoping to do is to be able to use this to replace some of the Intel control logic chips, so in particular the Intel clock controller, the 8284, and the bus controller, the 8288. Let's just see now whether or not we can program one of these ATF750Cs. So what I've done here, I've taken the gates PLD that were used from the samples originally, which was converted into 22V10, and now I've converted into the V750C, which I think is basically just changed the GV2210 to a V750C. So this basically has the two inputs, has the various logic outputs with an output enable defined, which we've used previously, and is based on the sample that's provided for the ATF16V8. So what we're going to do is to compile that. We just need to turn the project view off, otherwise it will crash. Okay, compilation successful. We'll just check the documentation file for that. So you can see we've got our various product terms, so the AND, the inverted values, the NAND, the NORs, the ORs, the exclusive NOR and the XOR. We can see our symbol table and the fuse plot. So you can see that there is extra fuse settings here for the mode and various other configuration settings here. Should say that the fuse number is not provided on the datasheet for the ATF750C, although from this information here we could actually work it all out and annotate it to actually provide that information, but it shouldn't really be necessary. And again, down the bottom here we can see the A and B inputs, and then we have our outputs there. So this is the T56 programmer, so it's a bit different from the TL866. So this is the TL866. One of the main differences to notice is that when you're using this one, you put the chip with the pin 1 at the top here, whereas with these ones, then the pin 1 is generally goes halfway up here, so generally you want the bottom of the chip flush here, so that's just something to be aware of. It does also have an on-off switch as well, should you want to, and does much wider variety of modern chips, including the 750C. I have been trying to get, this is a 2500C that I've got, a 40 pin, but I haven't been able to get that to work yet. So what we're going to do is to run up XG Pro, and we just need to choose the correct chip. ATF750C DIP24. There are some legacy modes for supporting older JEDEC files and things like that, but this is the one we want. Just need to read the chip first. It's always a good idea to read the chip first before we do anything with it, so I'll just need to load that file again. 750C JED. We'll program it and disable the lock bit. Okay, so that's finished programming, and I have still got the test here, and because this is a pin for pin replacement for the ATF22V10, I can actually use the test that I did for this. So you can see here we've got the ATF22V10C gates, and this just has all the various combinations for the highs and lows we've got down here. So if we're able to run the test and it runs and passes, then we know that it's working okay, which it is. Now when I try the same sort of thing with the 2500C, then basically I get all sorts of strange things coming back. Virtually none of the pins seem to be working properly, so I'm still going to look into that, but for the moment this is the one that we really need. The biggest issue that we've really got is that because of needing to have multiple clock terms for doing some of the more complex logic, then The 22V10 is not really sophisticated enough to be able to do that, and I'll explain why that's important now. So what we've been able to show there is that we've done a bit of an introduction to the 750C. It's got a lot more flexibility, and what I'm hoping to be able to do with this in the next video, the current designs for the breadboard PC use the Intel 8284 clock controller and the 8288 bus controller. Now, these chips are quite difficult to get. You certainly can't buy any recently manufactured ones. They're only generally available through eBay, through second-hand, and whilst they still are a number of them available, they're not necessarily always very cheap, and also a lot of the functions of them you don't really need. So in fact, the bus controller, I think if we run the 8088 in minimum mode, then we can largely eliminate the need for the bus controller. So in the next video, what I'm going to be doing is looking at what these clock controller and bus controller chips actually do in the breadboard PC, and how we can actually replace these two chips with one 750C. So the things we're going to need to be able to do is take in the input clock. So the original PC clock was 14.317 megahertz, and you need to divide that by 3, but with a 3367 duty cycle. We need to ensure that there's the correct timings for reset. We need to ensure there's the correct timing for the ready output, which also handles wait states for slower devices and memory. And what I'm going to do is to compare the original 8284 with the same input clock with the replacement that I'm programming to see whether or not it actually is a close enough sort of replacement. And what that should hopefully mean is going forwards, as long as you can afford a £300 programmer for the chip, you don't have to go out and source these legacy components anymore. We can actually do it using modern components. So thanks for watching. If you don't want to miss out on future videos, please hit subscribe, and if you found the content useful, please hit like. It just helps to make the videos available to more people. Thanks for watching.